Okay, so the next section is on the chromatic number of a graph. Right, so we have already looked at the concept of vertex colorings. When we looked at Kuratowski's theorem, we asked the question, what's the smallest amount of colors that I can use to color the regions of a map so that no two adjacent regions receive the same color. Now, two regions were said to be adjacent if they share a common boundary. Now, we use graph theory to model this. We placed a vertex in each region and we joined two vertices only if the regions that they represent receive the same color. So that was a coloring problem, and now so essentially it was essentially looked at colorings in planar graphs. So we are going to look now at colorings in graphs in general, and that brings us to the chromatic number. So what is a coloring? A coloring of a graph G is an assignment of a color to each vertex such that adjacent vertices receive different colors. Now, for the natural number k, a k coloring of G is a coloring with not more than k colors. So you can essentially see a coloring as a function from the vertex set of G that to each vertex is mapped to a natural number where the natural number goes from 1 up until k if we're looking at a k coloring. And this function assigns each vertex a natural number between 1 and k, and it does it in such a way that if you have different vertices and they are adjacent, the color that they are assigned, or the function values, are not the same. Right, so again, we usually assign not actual colors but positive integers to the vertices. So basically a k coloring is just a function from the vertex set of G to the set of natural numbers from 1 up until k, such that the function values of f and the points u and v respectively for different vertices, they are not the same whenever u and v are adjacent in G. Okay, so that's what basically a coloring is. Okay, now please note that we are only introducing the concept of a coloring. There are actually many different types of colorings. In the literature is quite extensive, and there are many variations on colorings. For example, we are looking at the case where two adjacent vertices, we're not allowed to assign them the same color, but you can extend this idea to include vertices at distance 2. So you can you have a distance 2 coloring. So you can assume that, you can put the requirement on that vertices that are at distance 2 from one another, or at most 2 from one another, they're not allowed to receive the same color. And I mean, that's got many applications in data transmission and many other applications as well. But we will only look at distance 1 colorings. So again, the next definition, given G and a natural number K, we say that G is K colorable or K chromatic if I can find a coloring where I can use K colors. Right, so the smallest possible value for K, or rather the smallest K for which G is K colorable, that's called the chromatic number of G, and it's denoted by chi of G. Right, so again, you take a graph and you color it. The question is, what's the smallest number of colors that I need to color the vertices of a graph? so that no two adjacent vertices receive the same color. You want to minimize this value k, and that minimum value is what is known as the chromatic number. Now, in case of a tree, here's an example. You can see that this particular tree can be colored with two colors, so that no two vertices receive the same color. Now, I mean, you can see it this way, like a tree will always have chromatic, if you look at a tree will always have chromatic number, 2. Well, at most 2, because you could include an isolate. So for a tree, you have the chromatic number is always at most 2. And the reason for that is trees are bipartite graphs, so you can always divide the vertex set of a tree into two partite sets, and you don't have adjacency within those partite sets. You only have edges between the partite sets. So you color the one partite set with color 1, and you color the other partite set with color 2. Right. So that is how it works. So we're going to study the chromatic number. Right, then another definition is given a coloring for integers between 1 and k, the set of vertices that receive color I is called a color class, and it's denoted by VI. Okay, so that's pretty straightforward. And just an observation, given a coloring of G, each color class is an independent set, as I explained previously in the lesson. So, I mean, that's obvious. So these are coloring is just a vertex partitioning problem. You're partitioning the vertex set of a graph into independent sets. That's essentially what you're doing. Right, so the next observation is that the chromatic number always lies between 1 and n. And that's very straightforward to see, because you're always going to need at least one color to color the vertex set of a graph. And you're never going to need more than n colors, which is the order of a graph. And that's pretty straightforward, because you can just take a graph and you can just color each vertex with a different color, and if you've got you'll never have adjacency if each vertex you'll never have the adjacency problem if each vertex receives the same color. Okay, so this theorem as well, it is quite straightforward. The chromatic number of a graph is 1 if and only if the graph's edge set is empty. And the chromatic number of a graph is n if and only if G is complete. So the first one is easy to prove, because if the chromatic number of a graph is 1, it means I can color it with one color. As soon as there's an edge between two vertices and I've colored every vertex the same color, you're going to have two vertices being adjacent receiving the same color. So that's impossible. So again, if chi of G is 1, then there exists a one coloring of G in which all vertices receive the same color. And since no two vertices receive adjacent vertices receive the same color, G has no edges. Okay, so that's straightforward. If G has no edges, then obviously you can assign each vertex the same color. So what happens if the chromatic number of G is n? If the chromatic number of G is n, why does it then imply that G is complete? Well, right, so there's your graph. Let's, for argument's sake, assume the colors are, the chromatic number is n. So therefore each vertex is colored a different color, and then you're going to see what's going to happen. Um, and we have to prove that G is complete. Now, if G is not complete, what does it mean? It means there are two vertices that are not adjacent, right? So let's say that those two vertices are not adjacent. Right. So again, you take the yellow color away, and you can basically color those two vertices the same color. There's no edge there, so you are not going to have a problem. And so therefore this graph obviously has chromatic number cardinality at most n-1, so that's going to be a contradiction. On the other hand, the graph G is complete, then obviously you're going to be forced to use n colors. If you can get by with coloring a complete graph with n-1 colors, you're going to get a repetition of colors somewhere. Alright, so it's pretty straightforward. So that's a characterization for when the chromatic number of a graph is 1 and when it is n. Okay, so then we just have this concept of NP completeness. There is no efficient method for determining chi of G, and so therefore it is NP complete. Now, in computational complexity theory, a problem is said to be NP complete when it can be solved by a restricted class of brute force search algorithms, and it can also be used to simulate any other problem with a similar algorithm. Now, although a solution to an NP complete problem can be verified quickly, there's unfortunately no known way to find a solution quickly, right? And so one is very often forced to use approximation results to see where a specific parameter lies, and that you'll see this a lot with coloring parameters and many other parameters in graph theory. Although you can't determine it exactly, you can find approximations. So essentially, any upper bound or lower bound is sort of that's an approximation. Next, we have just an example here for how do we prove equality. So take C5 as an example. How do we show that the chromatic number of C5 is exactly equal to 3? Well, what you're going to do is you're going to show just like with a crossing number, you're going to show that the chromatic number of a C5 is at most 3. And then what you're going to do is you're going to run through all possible colorings of C5, and you're going to show that neither 1 nor 2 colors is going to cut it. You cannot get away with 1 color, and you cannot get away with 2 colors. Once you've done that, you need at least 3 colors, and you get your lower bound. So again, can you color? First of all, you can color C5 using 3 colors. All right, there's C5. So let's take the first color. And what we're going to do is we color that vertex red. Then we take the second color, and basically we color the second vertex yellow with that color. Then we can use the red again, and then we can use the yellow again. Okay. Right, now the last vertex, can't use yellow, can't use red. We are unfortunately forced to use purple. So, right, so so you can see that this is at most 3. Now you just have to show that it's at least 3. Right, can we color it with one color? Obviously not. Right, you're gonna color all immediately. You're gonna get 2 adjacent vertices with the same color. Can you get by with 2 colors? In other words, can you partition the vertex set of a C5 into 2 partite sets where you don't have adjacency in the partite set, you only have edges between? Well, it's an odd cycle, so you can definitely not partition it into 2 disjoint independent sets. Alright, so again, you cannot color it in that way. Okay, so because C5 is an odd cycle, you cannot partition the vertex set of G into 2 independent sets. So therefore, the chromatic number of G is at least 3. Okay, so you've got equality. You've got equality. All right, so that brings us to what I've talked about. We say that a graph, there you can easily verify that. The chromatic number of a cycle on n vertices, I mean, that's going to be 2 whenever n is even, and it's going to be 3 whenever n is odd. That you guys can go and verify. The same argument applies. The chromatic number of Cn when n is odd, you cannot get by with one color, cannot get by with 2, definitely not with 2, because an odd cycle, you cannot partition an odd cycle into 2 independent partite sets. That's impossible. So it's always going to be 3, and you can get by with 3 colors easily. And then also for an even cycle, well, there you can partition an even cycle into 2 independent partite sets. And again, you cannot get by with one color, so it's exactly equal to 2. So that just brings us to this theorem here, and that theorem states that the chromatic number of a graph is 2 if and only if G is bipartite. All right, so let's assume that the chromatic number of G is 2. So we get 2 color classes. Right now, that means that we have a situation here where all these 2 sets are independent. Okay, and therefore we have the 2 color classes that we are talking about. We're coloring those vertices all the same color because we don't have adjacent vertices there. Okay. Now again, as I stated, you could only get maybe like edges between vertices there. Okay. Like that. Like that. But you do not get edges there, okay, because those are independent sets. So obviously the graph is bipartite. Now, if okay, so if the chromatic number is 2, that is going to imply that G is bipartite. Okay, obviously. Okay, and if G is bipartite, then it's clear, right? So if G is bipartite, then it means you can if G is bipartite, you can again partition the vertex set in G into 2 partite sets, and again, you don't have these partite sets are going to be independent, and you can, I mean, you only have edges between those sets there. And this means then that, again, what you can do is you can go and color the vertices in the one partite set with one color. Okay, and you can go and color the vertices in the other set again with the same color. Okay, so what does that mean? It pretty much means that the chromatic number of the graph G, the chromatic number of G is 2. Okay, so it's 2 if and only if the graph is bipartite. Right, so recall, G is not bipartite if and only if G has an odd cycle. Remember that result. Graph can only be bipartite if it has no odd cycle. So consequence of that result is that the chromatic number of a graph is at least 3 if and only if G has an odd cycle. And again, if the chromatic number of G is at least 3, then if it happens that G has no odd cycle, then G is going to be bipartite, and if it's bipartite you can color it with 2 colors, which is a contradiction, and vice versa. If G has an odd cycle and the chromatic number of G is at most 2, then it is going to be bipartite, or it's going to have no edges. And if it's bipartite, then its chromatic number is 2, which is a contradiction, and if it has no edges, its chromatic number is 1, which is going to contradict the fact that G is an odd cycle. So therefore that little result holds there. So let's just look at the following example as an illustration of how we can use this result to establish the chromatic number of this graph here. So the graph below is odd cycles, so we know the chromatic number is at least 3. We don't have to check the other cases. But is the chromatic number equals to 3? In order to establish that, can we find a coloring of the vertex set of this graph with 3 colors? So one can see there are, this graph has got quite a few cycles, odd cycles, right? So you can go and color we know what the coloring on these 3 cycles need to look like, right? We know they need to receive different colors. So we can color this graph strategically bit by bit. Right, so there we start. We start with that cycle C3, and then we move on to this C3 here. Okay, this C3 here, we need to color it that way. We don't have any other options. And then that C3 there, if you've already colored, you've used color 1, 3, and 2, and you will then be forced to color that last remaining vertex with color 2. Right, then you have to color that vertex. You have to color it 1, you don't have any other option, and then you have to color that vertex with color 3. Again, you don't have any option because you already fixed that color and you fixed that color there. So you can carry this process through right until the end. You're going to be forced to use those colors in that sequence, and then again you end up with a vertex that's already adjacent to all the 3 colors you used, and therefore you have to color that vertex with a 4th color. So I mean, this particular coloring you have here, that's the only coloring you can choose. I mean, you can obviously switch the order of 1, 2, and 3, but you're always going to end up forcing that coloring. So you cannot color this graph with 3 colors. So therefore the chromatic number of this graph has to be at least 4, and because you've demonstrated a 4 coloring, the chromatic number must be exactly 4. Okay, so the next little proposition is can be easily verified. If H is any subgraph of G, then the chromatic number of H is always less than or equal to the chromatic number of G, and that's obvious because if you take a coloring if you take a coloring of the vertices of G that's equal to the chromatic number, then taking any subset of the graph, if you take any subgraph of G, you've already established that coloring. You can then count the colors or the number of colors that you used in the subgraph H, and that will definitely be at most the chromatic number of G. So it's pretty straightforward that. Then we want to establish some initial lower and upper bounds on the chromatic number. Recall the click number of a graph. The click number of a graph, G, is the order of the largest click. And click is a complete graph, right? And it's denoted by W of G. Okay. The previous example we did, the click number of that graph, if we go back there, the click number of that graph, what's the cardinality of the largest click? Obviously, the largest complete graph you get here is C3. Okay, so click number of G is 3. Now it turns out that the chromatic number is always at least the click number of G, and that's also easy to see because if you take a graph and you look at a subgraph of this of G, and you look at a click, the largest click subgraph of G, and for this section of the graph, you're always going to need the amount of colors you're going to need for that section is going to be the same as the order of this click section. Right, so you always need at least so many colors to color that little section of the graph. So there, quickly, you've got an illustration. G, there's G, and H is the largest click. That largest click you get, we have to in that case use that number of colors. There is no way that you can get by with use fewer. Okay, so you have to, for that click, use at least 5 colors. So I mean, again, this the chromatic number of G is going to be at least the click number of G, and in case this click number in this special case is 5, right? So it's always going to be that case. You can't get away with any fewer. So the chromatic number is at least that click number. Then we're going to find some upper and lower bounds for the chromatic number in terms of the independence number. Now just recall that an independence set is a set in which we have pairwise non-adjacency. In other words, independent set is just any set of vertices where there are no edges between vertices in that set. Right, now the largest cardinality of such a set, independent set, that's called the independence number, and it's denoted by alpha of G. Some textbooks use different notation, but normally it's denoted by alpha of G. Now, if G is a graph of order n, and it has independence number alpha, then we have that the chromatic number lies between these two quantities, right? Okay, now why is that the case? We're just going to investigate that quickly. Right, so let's look at the lower bound first. So let's assume that the chromatic number of the graph is K, right? and therefore we can partition the vertex set of G into k partite sets. Now these sets that I'm talking about here, each one of them is independent, right, by the definition of colorings or chromatic number. So I mean, I cannot have, say, an edge there. I cannot have edges between vertices there. I cannot have edges between vertices there, okay? So, so let's observe the following. Okay, so each color class, the cardinality is at most the independence number, right? And this is obvious because each one of these color classes is an independent set. So each one of the, and alpha of G is the largest independent set. So these cardinalities are always less than or equal to the independence number, right? So if we just go and count the number of vertices, we get, if we take the sum over all the cardinalities, then you're going to end up counting the order of the graph. So you're just pretty much summing over all these partite sets, not partite sets, but over all those individual sets. It's a partition. Okay, now from there we can then say that this sum is at most. It is at most k times alpha of G, because each one of these terms is at most alpha of G, right? So from there we have, remember we said that's equal to n, okay? So from here we basically have that n is at most k times alpha, and so from there that implies that that the chromatic number of the graph is at least n over alpha of G. Right, next up we've got the concept of color criticality. Now color criticality is important because it's going to enable us to prove some upper bounds for the chromatic number. So it is often useful to consider graphs with a property that removing any vertex or edge reduces the chromatic number, and that's what color criticality is all about. We say that a graph G is color critical if for every proper subgraph of G, H, the chromatic number of H is strictly less than the chromatic number of G, right? And again, as I said, this must hold for every proper subgraph H of G. Now we say if G is color critical and its chromatic number is K, then we say that G is K critical or critically K chromatic. K critical is the more preferred term that they use, but you can use either one of the two terms. So let's look at an example. K2 is the only two critical graphs. So if you look at a two chromatic graph, that's a bipartite graph. Now, when will a two chromatic graph be critical? It will be critical whenever I look at a proper subgraph of the graph. The chromatic number of that proper subgraph must have chromatic number less than 2. So let's look at this graph and the bipartite graph. And let's say that G is 2 critical, right? So what must it look like? Okay, now obviously you must have at least one edge between the two partite sets, right? If no edge exists, right? If no edge exists, then the graph is not too chromatic, because you can then color, you can just use one color, okay? So therefore there must be at least one edge. Right, so let's call this edge XY, right? Okay, so basically, because this graph is too critical, it means that I can remove any number of edges and vertices, and the resulting graph will have a smaller it will have a smaller chromatic number. Now, can this happen? Can we have vertices there and vertices there? And the answer is, well, what happens if I go and delete all of that? What happens if I go and delete, say, that and that? Well, the resulting graph is still going to have a chromatic number 2. Okay, so basically what I have there is you can't have that part cannot exist, and that part cannot exist, since otherwise the graph will not be too critical. So again, if you look at G now, G is a K2 and it's too colorable. And if I delete, say, X, then you can see that the chromatic number goes down. And likewise, if I delete that, the chromatic number goes down. If I delete the edge, chromatic number goes down. So therefore, K2 is the only too critical graph. Okay, so for the case where K is equal to 3, that means that lambda of G needs to be at least 2. So every 3 critical graph must be 2 K minus 1 edge connected, which is 2 edge connected. Now you can easily prove that. Right, so let's say it's not the case. Let's say the graph G, well, we're given that the chromatic number of G is 3, and G is 3 critical. Okay, and let's suppose that it is not 2 edge connected. We know it's connected, so therefore it's not 2 edge connected, meaning that I can remove somewhere an edge of this graph, and it will result in a disconnected graph. So therefore this graph is a bridge. This graph has a bridge. Now because G is 3 critical, it means that if I go and delete this edge, then each proper subgraph is going to have smaller, it's going to have chromatic number smaller than 3. Okay, so the chromatic number therefore of G1 is at most 2, and the chromatic number of G2 is at most 2. Okay, so I can use, at worst case scenario, I have to use 2 colors for G1 and 2 colors for G2. So, right, so what we're going to do is we can find some 2 coloring there of vertices of G1. Okay, and then for okay, so let's say what happens is now we've done our coloring, and we've colored it, and then adding the edge back. That is going to be a problem, because this is going to imply that the chromatic number of G is in fact not 3, but it is 2, which is a contradiction. Okay, so what must happen is Y must receive the red color. Okay, Y must receive the red color. Okay, but what I do now is I can just go and recolor G2. Right, and I do this by permuting the colors. So I'm going to take the color of Y away, and I'm going to color it yellow. Then I'm going to take the color of that vertex away, and I'm going to color it. I'm going to color it red. Then I'm going to take the color of that vertex away, and I'm going to color it with that color there. So I'm just permuting the colors, therefore once I join that edge back again, you'll see that I've constructed a valid coloring, and so the chromatic number of G is at most 2, which is a contradiction. Okay, so basically this graph cannot have a bridge. I have to remove at least 2 edges for the graph to become disconnected. Right, so how do we prove this? How do we prove this theorem in general? Okay, so we looked at 2 special cases where k is equal to 2 and k is equal to 3. But it turns out you can generalize this type of argument. So how do we prove that the edge connectivity is at least k minus 1, where k is a chromatic number and G is k critical? Right, so what you do is you take the graph G, and basically what we do is we delete, we let S be an edge cut, right? An edge cut equals to lambda of G. Now what is this edge cut? If I remove these edges, that's my what we're going to do is we're going to delete those edges, and we're going to have 2 graphs that result, G1 and G2. Now G1 can be colored with at most k minus 1 colors, or we can color G1 with k minus 1 colors, and we can color G2 also with k minus 1 colors. Right, so this is G1, okay, and that section there is my graph. That's G2. Okay, and again, like I said, you can use k minus 1 colors to color G1 and G2 respectively. You can use the same colors. So now let U1, U2 up and U3 up until UK minus 1, let that denote the color classes, and W1 up until WK minus 1 denote the color classes. Now, if we look at color 1, right? If we look at U1, and we look at W1 plus 2, right? Now, how many edges are there between color class U1 and W3? There is this edge here. We count that edge there, right? And let's call this this index I, let's call that index 2, right? So again, the number of edges between U1 and W1 plus I is, in this case, 1. If you look at the second color, U2, the color used in U2, how many edges are there between U2 and W4? Okay, so here's U2, and edges, well, we haven't indicated that yet, but we go and count those number of edges. And you go up until you get to uj minus 1, and you look at all the edges between uj minus 1 and color class wj minus 1 plus I. And you carry this process through until you get right to the last color uk minus n. With each time you count those number of edges. You throw all those, and again the indices you mod by k minus 1. And you throw all those edges in a set S, and you call this set S subscript I. So S subscript I corresponds to all those the edges that you counted. Right, so if you look at as the special case where k minus 1 is equal to 4, then if we look at S1, S1 is going to be, so you look at, you count all the edges between UA and WA plus I, and then you remember you're taking, you're modding that by k minus 1. So for U1, you go and count all the edges between U1 and W2. In this case, that's empty there. Then you go to U2 and you count all the edges between U2 and W3. Remember, the index I is 1. So then you count all those edges, that's empty. Then U3, again, you count all those edges there. And then U4, you're counting the number of edges between U4 and W4 plus 1 mod 4. So you're counting all the edges between U4 and W1, and that's how you work it out. So in that case, it is clear that S1 is empty in that case because we've not counted any edges. Now for S2 equals 3, for S2, now your index I is equal to 2, so that is what it's going to look like there. You're looking at the number of color edges between U1 and W1 plus 2, which is W3. You're counting no edges there. Then you're looking at the number of edges between U2 and W2 plus 2. There you've counted one edge. Then you look at the number of edges between U3 and W3 plus 2 mod 4. 5 mod 4 is you're looking essentially at the number of edges between U3 and W1. There you've counted another edge. And then lastly, you're counting the number of edges between U4 and U4 plus 2. 4 plus 2 mod 4 is 2. So essentially you're counting the number of edges between U4 and W2. And there you've counted another edge. So in total, you've pretty much counted 2 edges. Okay? So that's how these sets, the S sets, are defined. Now what they claim is that for some index I, where I runs from 0 to k minus 2, for some I, we have that some Si is not empty. Okay, what happens if it is the case? What happens if some Si is in fact empty? So for argument's sake, let's assume S1 is empty. The proof is the same for all indices I. So let's say S1 is empty, right? So there are no edges between U1 and W2. There are no edges between U2 and W3. There are no such edges. No edges between U3 and W4. There are no edges between, up until the end, between UK minus 1 and W1. Right, now because there are no edges there between those two partite sets, it means that I can pretty much do the following. I can basically take the colors the color that I use in W2, and I can replace it with the color I used for U1. Right, like that. Now, if I look at U2, because there are no edges between U2 and W3, I can go and replace the colors of W3 with the color that I used for U2. Like that. Because there are no edges between U3 and W4, I can go and replace the color I used in W4 with the color I used in U3. Let's say, for argument's sake, there I've done the replacement for that particular set there. Okay, and let's call that W4. Right, so I can carry this process through right up until the end. If I go up until uj minus 1, now uj minus 1, I can go, because there are no edges between uj minus 1 and wj, I can color wj with the same color that I used for uj minus 1. Like so, and then if I go to uj, there's no edges between uj and wj plus 1, so I can color the color that I used in uj. I can color the vertices of wj plus 1 with that color. Right, like so. And then once I get to the end, UK minus 1, because there are no edges between UK minus 1 and W1, means I can color the colors of W1 with the color I used in UK minus 1. Like so, alright? And also, again, I would have changed this color as well, because I would have looked at the color I used in UK minus 2, which would have lied there, and that color I would have used there would have been that color there, and so I've pretty much sort of just permuted the colors here, and I will not have any problems here with edges because these sets are all independent sets, right? So I'm not going to have any issues there, and I've basically constructed a coloring that where I'm only using k-1 colors, and we said the graph is k chromatic, so this is impossible. So therefore, we cannot have a situation where one of these S's that are defined is empty. Every one of these S's must have at least one edge. Now, it is obvious that all these SIs are disjoint because of the way that they are chosen, these indices, right? So because these SIs they only count possibly partially the cardinality of S, it means that S is at least the sum of these respective cardinalities. Right, so therefore, because each one of them has got at least one edge in, you're going to count at least k minus 1 edges. So therefore the edge connectivity of G is at least k minus 1. Right, so this corollary states that if G is color critical, then the minimum degree of G is at least a chromatic number of G minus 1. That follows from the previous result. Because the edge connectivity of G we know is at most the chromatic number of G minus 1. Okay, and remember the edge connectivity of G is obviously at most the minimum degree. Okay, because I can delete the edges incident with a minimum degree vertex, and that's going to give me a disconnected graph. So because lambda is the minimum number of edges I must remove for disconnectivity, it's therefore at most the minimum degree of G. So you can basically then just replace that with an inequality, and you can deduce that delta of G is at least that. Okay, now if G is color critical and S is a subset of G and S is a vertex cut of G, then the subgraph induced by S cannot